So this is the first podcast of Unit 4, where we're going to be talking about how to name different types of chemical compounds, and first thing we have to be able to do is tell these different types of compounds apart before we can name them differently. So that's what this podcast is about, the different types of bonds we have and some of their properties. So this is going to cover pages 2 and 3, pretty straightforward. And we're starting by talking about why chemical bonds even form. It's because when these atoms get close together enough to exchange electrons, it lowers the energy of each individual atom. It releases energy, and those two atoms form that chemical bond. This bond, this lower energy state, is what holds the atoms together, and two atoms being held together is what we call a compound. So, important to bring back that vocab from Unit 1. Now, right underneath that definition, we have a little kind of graph that's upside down and backwards on yours, but this is just showing that the closer our atoms get, there's this sweet spot kind of where they're at the lowest possible energy at this perfect distance, this Goldilocks region there, and it's close enough for the electron clouds to start to overlap, but the nuclei aren't actually hitting each other, and we see here that lower energy state is where those atoms are most stable. They'd have to put forth energy and use up some energy in order to get pulled apart, to pull themselves out of that kind of valley there. So that's just why they form. You probably don't need to worry about this graph too much in general. Now, electronegativity, we just talked about this, is a measure of an atom's ability to attract electrons in a chemical bond. So this is going to come back into play mostly in telling the different types of compounds from each other, because depending on what combination of elements we have, if atoms really like to hog electrons or they like to give them up, that electronegativity difference between them is going to determine what type of bond we have. Now, we are going to be classifying things as ionic and covalent, but it's important for you to understand that it's a spectrum. It's not ionic is not covalent at all. There's no sharing happening. It's relatively kind of squishy. There's going to be some times when it's a little bit of both, but we're going to classify them and keep it black and white for this unit. So there's this periodic table, which is also upside down and backwards. We honestly don't need it that much, but we will come back to it in just a second when we do, for a brief moment. Now, we can tell the different types of bonds by their electronegativity difference. And if the electronegativity difference is large, it's a big difference between our atoms, then that's when we're going to have an ionic compound. Now, technically, that means the electronegativity differences between 1.7 and 4.0. We'd have to use that periodic table, subtract the two different element values to find this number, but that's not really what matters. What matters is this large electronegativity difference comes from there being a big difference between our elements and their types of elements. So these ionic bonds are going to be happening between a metal and a non-metal. Very different elements, very big electronegativity difference forms that ionic compound. With kind of a medium electronegativity difference, we have what we call polar covalent bonds. And these are going to be happening between different nonmetals. So they're closer to each other. They have a smaller electronegativity difference between 0.3 and 1.7, but it's still going to be covalent. It's just kind of a middling difference. And then we have a very small electronegativity difference, anywhere between 0, meaning not different at all, and 0.3 is going to be non-polar covalent. And this is only going to be happening generally between two identical nonmetals. So between two atoms of oxygen or between two atoms of nitrogen. Those have no electronegativity difference, and so those are going to be non-polar. There are some different elements that can bond that have a small enough difference to form these non-polar covalent, but in general it's going to be what we call diatomics, and we'll talk more about those later. So, on the periodic table, the important part isn't all these numbers. I'm never going to ask you to subtract different numbers and to declassify bonds as ionic covalent and polar covalent. What we want you to look at is whether metals and non-metals. So just remember, metals are to the left of our staircase, everything over here. And our non-metals are to the right of the staircase, everything over there. And honestly, from now on, we're going to just kind of generalize and say that there are no metalloids. It's just metals and non-metals, so that we have those differences for our types of bonding. So, with these examples of elements and trying to classify the type of bond that they have, we could look at the electronegativity difference from those numbers on the table, and the difference between I and I is 0. We could also look at the type of elements they are and see that this is two identical nonmetals, and either of those things would help us classify it as nonpolar covalent. K and F has an electronegativity difference of 3.2, 4 minus 0.8. But we can also see that K is a metal, an alkali metal, F is a nonmetal, and that means that it's ionic. Same with calcium and oxygen. I already know that those are a metal and a nonmetal, so I don't care that the electronegativity difference is smaller. I don't have to worry about, where's the dividing line? Is it like 2 something or is it 1 something? If it's a metal and a nonmetal, it's going to be ionic. And then here I see our H and C, which do have an electronegativity difference of 0.4, and that is 2 different nonmetals, so either way, that would get classified as polar covalent. So these are the ways that we can classify our different types of bonds. And like I said, I'm not going to ask you to use those table of values or memorize those different kind of division points between the types. It's just going to be based on the types of elements. Now, it asks us right below this, which has the most covalent nature? And that would be the non-polar covalent, which in this case is our iodine and all of the other diatomic elements. I said we'd talk about this more here. There are 7 different diatomic elements on the periodic table. And actually, if we go backwards a couple places, then you can find these diatomic elements if you start at element number 7, which is nitrogen, and you make a 7 shape, then all of these elements here, I'm trying not to include that astatine, I went down a little too far. These are the elements that are diatomics. So start at 7, make a 7, and then you've outlined all of the diatomic elements on the periodic table. There's other ways to remember it though, like this crazy word Brinkelhoff is made up of those 7 elements symbols in a random order. It kind of sounds like Hasselhoff. It's just a cool sounding word. Maybe you remember it, maybe you don't. Or this saying, I bring clay for our new house. Another way to remember those same 7 diatomics. They're always going to have a buddy. They would die without another atom there with them. It's kind of like those girls that can't go to the bathroom by themselves. They can't go to the lunchroom by themselves. They've got to have a buddy. So much so that they make one out of thin air if they need one. So these elements most of the time are going to be floating around with a buddy of a different element, like sodium chloride, NaCl, is a common compound for chlorine to be in, but if you take the sodium away, the chlorine's going to freak out and say, but I have nobody. It's going to grab onto another chlorine. So it's always going to be bonded to something. At the very least, it'll bond to itself, to another atom of the same type. So work on remembering those 7 diatomics. And we can move on to the next page and try and finish this up. So these 3 different types of bonds. We talked about ionic and covalent. Metallic is the other type of bond, and you might have realized I'd left that out. I talked about metals with nonmetals, and then 2 nonmetals. I hadn't talked about 2 metals yet, because these aren't technically really bonds, and we'll talk about that more. But these are the 3 different types of compounds, combinations of elements that we can make. And ionic bonds are made up of a metal and a nonmetal, a giver and a taker. And because of that, the electrons gets transferred from the giver to the taker. Our covalent bond is 2 nonmetals, 2 atoms that both want electrons. So with them both fighting over these electrons, what ends up is that they get shared. And they're not always shared equally, like you can see from this picture. Nonpolar covalent, between 2 atoms with the same electronegativity, they're sharing equally. Those electrons are in the center. But in a polar covalent bond, one of those atoms wants the electrons and has a greater attraction for the electrons in a chemical bond and is going to hog the electrons more. That makes it slightly polar. And then in metallic bonds, we say that they have a sea of electrons because these are metals. They all want to give up their electrons and give it to this other atom. And when it's just with other metals, everyone's trying to give everyone else their own electrons So they kind of just put them in a big wishy-washy sea of electrons where anyone can have the electrons at any time, and they don't really belong to anyone, but they just float around in this vast sea of electrons with these metal atoms interspersed in between them. So that's the biggest difference in these different types of bonds, and this is going to determine a lot of their properties. So, like we just talked about, metals and nonmetals make ionic compounds. Two nonmetals is our covalent, and any combination of metals is our metallic. Even just aluminum, a single element of aluminum has thousands, if not millions, of atoms of aluminum, and metallic bonding is what's holding those metal atoms together. Ionic compounds we actually call formula units, the individual kind of combination that matches their formula. We call them formula units. The special name for our covalent compound is molecules. So everything is compounds if it's made up of different elements, but ionic, those compounds can be called special names. Same with covalent. There are no special names for our metallic bonding units. So just some examples. You can see here we have our Na and our Cl, and it's important to note that the cation, the positive ion, is always going to be the first element, and the anion, the negatively charged atom, is always going to be the second element in the formula. So first is always positive, second is always negative. And you can see in this second example that I have kind of more than one nonmetal, more than one anion here. And that's actually what we call a polyatomic ion, and it's made up of multiple atoms, but we'll get into that later. As we go across some more examples of our covalent, these are nonpolar examples. You can see these diatomics. Polar have different elements, different atoms, all nonmetals still. And then we have these polyatomic ions that are actually covalently bonded because they're two nonmetals together. But then, because they have charges, they can go and form an ionic bond with a metal. Well, actually, kind of fun fact, this right here, this molecule, pardon me, this compound has some ionic bonding happening here between the Mg and the S, and then it has some covalent bonding happening over here between the S and all of those O's. So a ionic compound with polyatomics in them actually has ionic and covalent bonds formed. Then some metal examples. You could have plain metals like magnesium or iron, or a mixture of metals, and all of them have metallic bonding happening. So bond strength is measured by lattice energy, which is a physical change, bond energy for our covalent, and heat of vaporization for our metals. Actually not super important differences. It's how we measure these energies, and I'm not going to get into what each of these means or why. It's not something you're going to see again. These we are going to see again. So, the properties, the way I could say, ask you to go into the lab and classify different substances as ionic, covalent, or metallic would be based on these types of properties, like melting point and boiling point. Ionic compounds have really high melting points and boiling points because there's a lot of energy holding them together. Covalent have very low melting points, and in fact, some of those melting points and boiling points are negative because they tend to be liquids or gases at room temperature. Metals also have very high melting points and boiling points. At room temperature, our ionic compounds tend to be solids. Our covalent can be anything, really. It depends on some other factors there, but they can be solids, liquids, or gases. And metals tend to be solids. If you try and dissolve these things in water, you're going to find that ionic compounds are mostly going to be soluble. Covalent, if they're polar covalent, they are soluble. If they're non-polar covalent, they're not. And metals are not soluble. You're not going to throw a chunk of aluminum in water and actually see it dissolve. It might react with the water, like in the case of iron, it'll react with the water, form rust, and go away, but that's different than just dissolving in water. Now, conductivity of electricity and heat is kind of complicated with ionic compounds, because as a solid, just a chunk of salt is not going to conduct electricity if you put two wires up to it. If you melt that salt, now that's going to take 800 degrees Celsius to melt it, but if you melt it, then the ions can move around and carry that electricity, and it will conduct electricity. Or, easier, just dissolve that salt in water. That lets those separate ions move around, and then yes, it will conduct electricity. Our covalent tend to be poor conductors of heat and electricity, although sometimes if you can get something that's polar to dissolve, it could just maybe conduct a little electricity, but not much, not often. And then metals, you don't have to do anything to them. They are good conductors of heat, good conductors of electricity. So, there's a couple of questions down here at the bottom of the page that have to do with what we just talked about up top. Asks us why metals are malleable. Well, it comes back to those electrons. Remember, we said metals have this sea of electrons, and because those electrons can move and flow freely without affecting the metallic bond, you can smash it and smush those atoms into any shape you want, and the electrons are just going to flow and move freely with them. So the metallic bond isn't affected by the shape or the position that those atoms are in. And that lets them have a lot of very flexible properties. And then, kind of the opposite of that, why are ionic compounds brittle? Well, it's because the atoms can't move and flow freely. The electrons have been transferred from one place to another and created these ions. And if you move this crystal lattice at all, then you're going to get a positive ion happening to line up with another positive instead of with its negative kind of buddy, and two positives will repel, or two negatives will repel each other. And so if you just tap it wrong or hit it too hard or in the wrong direction, you can force the alignment of the lattice to change, and then it almost seems like this glass just shattered itself. You're like, I didn't hit it that hard, but you hit it the right way and the right kind of amount of energy to cause an itty-bitty change. And then the energy of having that bond kind of shifted is going to break the rest of that lattice apart. So, if you move those atoms at all, the charged ions repel each other and break the entire lattice apart. And then why ionic compounds are solids? It's because it has a lot of energy. It's a very low, very stable energy kind of state. So it takes a lot of energy to break that ionic bond. So you have to put that energy, that temperature, really, really high in order to be able to cause that state change to occur. And then if you do manage to melt ionic compounds, then they tend to conduct electricity, like we said, if it's molten or melted. And that's because electricity is flowing and moving charged particles that are moving electrons around. And if our ions are stuck in this lattice, then it can't carry those electrons. But as a liquid, those ions can move and flow and carry electrons just as easily as that sea of electrons in the metals. So that helps them conduct electricity. And that is officially it. So see ya in class.